Is that seawater?
Look at this, dude.
This is the most disgusting car I've ever touched. Okay, everybody, this is a very, very exciting day. I haven't talked about it very much, but that's because Semir and I have been doing a lot of figuring out, and I just wasn't in the place to go over every little detail because I wasn't even sure. So we are here at Gromm Racing to discuss the C8 engine. And this is not your regular run-of-the-mill LS, so I literally have to have Semir here to make sure I don't screw up by saying something wrong, because there is multiple engineers involved on this project. There's stuff that I haven't even heard of, and there's stuff that like is standard race engine stuff that I never even knew was a thing. So let's freaking dive into it. So I think the first place that we want to start is the block. Now, Concept Performance, they make the LSR block, right? You guys have seen that. That's what I use in the race car. We switched over to the LSR blocks after a couple of issues with failed blocks. And in the race car, multiple seasons, 0 issues. But this LSR block is special. It is not your standard anything. It is a tall deck and it is a raised cam. And the reason why you do that is to do big freaking cubic inch. And I'm gonna let Semir kind of talk about the highlights of the block and why we decided that we were gonna need this tall deck. Because for me, I've always stayed away from tall deck because supercharger bracket means that it places the head at a different location away from the crank, and there were just all these things for reasons for me to stay away from it. But we're doing naturally aspirated, so that changes things. That allows us to do big dick shit like a tall deck race cam block.
One of the reasons we chose the LSR block is, like he said, the race cam tunnel. So this engine, the displacement of this engine is going to be 463 cubic inches, which means we're going to be using a 4250 stroke in this. That stroke with the rod combo typically gets into the interference, especially when you go to a 16mm cam board like what we're going to do with this. The reason we do that cam board is so that we can use a larger diameter core, which gives us stiffness in that core. It'll allow us to rev higher, keep the valve train happier, all of that good stuff. We'll also be using these needle bearings for the cams.
Cam roll. See, this is another one of those things where, like, I've heard about it, I've seen pictures of it, but I've never had a roller cam bearing in my hand, and like this is some crazy stuff. Like your normal guy doesn't do that, you know?
Yeah. So the block still needs to be machined by Brad down at God, I better forget his shop's name, Brad Lagman. He's gonna take care of that for us. He'll open up this so that we can put those roller bearings in there. And then in addition to that, some of the valve train components that we're gonna be doing, well, let's stick to the block first. The material that is in this is a higher grade material than a factory block. We've got gusseting in there. Also, if we look at the bottom side of this thing, there's a couple benefits to it.
The main caps are just unreal in these blocks.
Main caps, but if you also look here on a factory block, they're typically windowed down here. So you're not gonna get that failure in that area, the cracking and stuff, because Carlos over at
and that's exactly where my blocks used to fail. Every time without fail, it would crack from the main cap up to the cam area, and then that's a $6,000, $8,000 block. That's done. Just done.
So and then they've got ductile iron sleeves in it. You get priority main oiling, and I'm not, for some of you, if you're not familiar with what priority main oiling is it means that the crankshaft gets oil first and the valve train is secondary to that. Typically on a factory block, the valve train will see the oil first, the crank and the rods will see it last. In a high RPM situation like what we're gonna have with Matt, you don't want that. And you know, you wanna get the oiling, especially with the dry sump system and everything like that. We wanna make sure everything's lubricated and stays happy down here. So in addition to those features,
because the reason why these things are important is because the whole idea with this is well over 1,000 horsepower, and just you keep, every time I talk to this guy, it's the power number, the goal keeps going up. Talking crank horsepower, we'll go see the engine dyno. His boys are setting up in there in a little bit. 9,000 RPM. That's the key here. That's the reason why we went way deep down this rabbit hole, because I was like, nah, it's gotta be, if we're doing 8-into-1 in the C8, we gotta have 9,000 RPM. That's mandatory. And then you go way deep down the rabbit hole, and this is where you wind up.
Yeah, Matt's just as bad as me. Both of us got together, we egged each other on for more and more and more. But that being said, another feature that the LSR blocks offers is they have the additional side clamping force on that. So, you know, keeping everything happy again in that bottom end. Let's see, other features. If we look at the lifter bores here, take a look there. What we're gonna do is we're gonna go from a standard 842 factory lifter bore. We're gonna take that out to a 937, or that's actually, I think it's about a 1-inch OD on that hole on the bushing. Then we're gonna use a keyed style lifter on there. So it reduces the mass of that lifter. So again, we're trying to reduce stuff, make it stronger, lighter for higher RPM applications.
This is another one of those things. I always thought there's two things that you do for lifters for LS. You have the stock lifter trays, right, which bolt right down the middle and use a factory lifter, or you throw that in the trash and you do a tie bar lifter. And then I asked Semir, like, yeah, those are the baddest shits right there. Which lifters are we gonna do? He's like, dude, no 9,000 RPM is happening on a tie bar lifter. Like, that's not a thing. So you get down to sleeving your lifter, and they're keyed. So this thing literally has a slot that each lifter is going to be keyed into so that it can't rotate.
Yeah, these aren't bushed or honed yet, so they'll be honed. Once we install them, we hone them to the size of, or just a bit over the size of the lifter so that it has the proper clearance, and then this will locate off of that key right there. Okay, so
freaking crazy.
They're also DLC coated, which gives you
oh, it's DLC. Yeah.
Pins will also be DLC coated. We don't have the pistons yet. We have to send the heads out to Race Tech, and they're going to take care of doing some custom pistons for us.
Yeah, these heads. Oh,
well, we haven't got there yet.
Yeah, geez. Well,
I jumped ahead.
We'll get. I mean, I guess it's time. Like we chose the best block available on the market for a damn good reason. We went over wise tall deck, raised cam, all the benefits. We have the meat and the capacity to do these lifter sleeves and all of that. And then the reason why we're doing that is this is key right here. This is how you do 9,000 RPM and make power all the way up there.
So these cylinder heads are based off an SC2 cylinder head, but this is what they're from CID. They're called the LSCR cylinder heads. So these that we have here are as cast. So they haven't been ported yet. We'll take a look at the CNC in a second, and I'll go over all of that. But basically, we're developing port program with the help of Cesar Talise from CT Porting, and you know, with all of our goals, our cross-sectional area, that flow that we need, all of those things are being taken into account. And then we've got these castings from John at CID. We'll end up CNC porting them, but so basically, this is a 400 bore spacing cylinder head that was designed off of a Ford cylinder head, an SE2. They flow just about 500 CFM if I'm not mistaken.
Jesus Christ, so crazy.
So they'll use a valve that's 2-300, but if you look at that real light titanium, these are from Exeldyne. So beautiful valve right there.
Yeah, this is a serious set of valves right here.
Intake valve. This is our exhaust valve here. Nice shape.
Damn, it's nice.
Airflow.
And something that it's so funny because this is so normal to Semir, right? But to me, and this is how we got here too. This is the start of the conversation. I was like, yo, what's the baddest cylinder head for naturally aspirated LS stuff? It's like, well, if you want to keep it basic, you do this brand, or there's these. But like, if you really want the big dick shit, like you got to do these. And the reason why they are leaps and bounds different and flow that much more is because the valve location.
Exactly.
That's what I'll break it down for somebody like you and me to understand. It's because these are not inline. An LS cylinder head usually has all the valves inline, and that's great. It makes the power that it does. But this is the next step, and they do this so that they can move the exhaust port around, the intake port around. All of it is changed at a totally different height. So although this is an LS pattern, right, that will bolt to this. There's nothing else LS left. It's a NASCAR Ford head.
Well,
that bolts to a block, right?
So they're a canted valve cylinder head.
Canted, that's what it is.
The benefit of this is because of the valve angle, they stand the valve up. So the combustion chamber can be a lot smaller, which makes it a lot more efficient. So the burn, and you want to get air in, but you want to burn it efficiently and turn that air into power. So you want to do it as efficient as possible. With the design, like a standard inline cylinder head, you have a 70cc chamber, you have a 12-degree valve angle on most stuff. So it's not as efficient as it can be. This head brings that efficiency up. It uses a really small chamber design. So we're gonna try to get as efficient as possible. But also, that raised, if you look at the raised runner, it's hard to tell like what that's going to look like after it's done, but we'll get to that.
Right. And we have a set of hand-ported heads that we are going to be kind of making I'll let Semir explain, but we're digitizing that head so that we can get that port program onto these heads, and then we are going to be doing the machine work ourselves on these heads, which further leads us down the path of like, this is a custom engine. Every single component has been talked to with a team of engineers, thought about. It needs real people who know what they're doing, which is why I'm here with Semir. And also like, that's why this and this, you were on calls with the rods and the crank. You were on calls with Callie's engineers just to figure out like something as simple as a crank and rod package, which by the way is not simple at all.
No, not at all. So I actually have a really good relationship with Nick Norris from Callie's. He's the lead, an engineer over at Callie's. I met him through a group that I'm in. It's called the Brotherhood of BTUs. We developed a relationship with that, and I told him about Matt's project and the project that we're working on. So we actually had a custom crankshaft built specifically for Matt's needs. In addition to that, he built us a custom set of rods, and I'll kind of go over some of the features of this crankshaft. It uses a standard main journal, but it uses a 2-inch rod journal, and what they did is they used a NASCAR thickness rod on that. They moved over the dowel, the locations for the bearings, so that we didn't have to do any modifications to the bearing so that it wouldn't touch the radius or kiss against the other rod next to it. But also when they narrowed this, what they were able to do is widen the thickness of that crankshaft so that the counterweights didn't have to stick out as far. So the moment of inertia is moved in more towards the center. It's a more robust crankshaft. It's a fully counterweighted billet crank as well. So it's
billet
a piece. There's a lot of engineering that's in this, and it's based off of their Ultra Dirt series crankshafts.
And when I heard that, I'm like, okay, Ultra Dirt, that's like a sprint engine, right? Like a dirt sprint style engine that makes big power, big RPM, ton of force that goes into the crankshaft. So the materials chosen to build the crankshaft out of has to be, like, take that into consideration. And that's what they put, that's this technology into this crankshaft, but which is kind of rare for an LS. That's not what they do for LSs, right?
No, I mean, this really took a lot from Nick, and he was totally invested in the project and everything like that. He had some CAD designs with the camshaft, lobes that we were going to use, everything to make sure that the rods wouldn't interfere with the cam. So I have to say, huge thank you to him.
Yes.
The time that he put into this deal. Like I've never had someone like help out that much, and it was awesome. So
and it's crazy to think, because the Callie's is the best in the business. We all know that they are the best in the business. So for them to put the time, effort, and energy into doing something like this, where we're all just trying to figure it out at the same time, and they took charge of the project, got it done in a reasonable amount of time, and made something that blows my mind. Like, this is crazy right here. This is it's called Ultra, but it has nothing to do with their traditional Ultra rods, right?
Yeah,
but when you feel this,
they're Ultra Dirt, but some of the features that they have in there are similar to the Ultra Dirt, but going to a custom. Like the length of the rod
is huge.
I gave him the length so that we could use a custom or a very common compression height piston that's within the market. So he did all of this stuff, and designed this, and just put so much time into this rod, and the features of it and everything. Again.
And as soon as I touched it, I was lighter, like, it should be way heavier than it actually is. Like, especially for how big it is.
And the thing is too, so if you look at it, the way he designed it so that it's more robust, but it removes weight out of it. It's got a little bit of a taper. You can feel, you can't see it. It's really hard to see.
It's crazy.
So there's mass here so that there's strength. This is your highest load area right here. Typically if a rod's gonna break because of tension or tensile, it's going to be right in this area. It's going to break, but he put the mass back in here. He tapered it back in to reduce the weight. It's a beautiful piece, and just like looking at it, you don't really see like what's in there. And then he also put L19 bolts hardware in there.
Yes,
all that good stuff. So higher clamping force, but it's still an affordable hardware. So like when you're servicing this engine down the line, it's not going to kill you to like replace the hardware on it. So
because that's a thing too. It's funny actually. Odie had an engine problem, and it was because of a rod bolt. And like, it was one of those things. We don't replace rod bolts. Like, that's not something that I knew was a thing. Is like, hey, you got to replace rod bolts. But after talking to the engineers at Callie's, they're like, no, that's just part of what you do when you tear down an engine. You do all the hardware.
Hardware has a lifespan, right? So it's stretched and in that force, when every time you clamp that down, you're stretching that, and then over the years of it holding this rod together, at some point there's going to be wear in it and replacing them and everything like that and servicing them. But what you'll do is you'll torque this up to their value that they tell you. You'll measure it and see how much stretch you get into it. So at some point, if you go to torque this up, say, I can't remember what the specs on this are. I think
like an 80 or something. Yeah,
80 foot, and then you get like 10th hour. You get 7th hour. You get more stretch than what you want to see in that. Then you know that the life expected, or the life of that bolt, that hardware, has gone. So you replace that. So you need to be aware of that, and then keep data on that as well. So hey, at some point I might have to replace this.
Yep.
And that's just cheap insurance. I mean, if you look at the big picture of everything that you're doing, rod bolt.
Yeah. Which is funny because like the price of that one bolt, it would probably surprise a lot of you as very expensive. But in the grand scheme of things, with all of this, how much effort went into all of this, that's cheap insurance. No doubt about it. No doubt about it.
Let's see, anything else? Oh, so let's talk about the rocker arm.
Yes.
So these are a steel rocker arm from Jessel that we'll be using a similar type here. But if you look at the design,
because these heads require like a proprietary valve train.
Right.
Like the only people that they work with to design this and make this is Jessel.
I think there's T&D also makes them.
Oh,
sorry.
Right, T&D.
T&D makes them, but I work with Jessel. We do a lot of stuff with Jessel. We've had a great success with Jessel. We've had great success with T&D. But yeah, so
it's funny too because you're like, okay, this is they know what's going on with this head. I'm like, let's get this stuff ordered up, Semir, and he's like, pump the brakes, Matt. All of it, it's all of calculation. So once we get the heads, you get it installed. There's like so many steps that need to go into just figuring out what the rocker ratio is going to be, the material that it's going to be made out of, right? Because all the weights and all that stuff really come into play. So much more than your average, just like, oh, I'm just going to buy a set of LS rockers, which is what I'm used to. I'm used to that off the shelf life.
The reason for that is when we design the camshaft, we want to know like, okay, what ratio rocker are we going to use? But a lot of that comes from the cylinder head, right? So once we digitize the head, we know average cross-sectional area, minimal cross-sectional area. We know what we can actually achieve, like our goal. Like looking at it and looking at airflow, that only gives us a small picture of what that cylinder head is going to do. And if someone says, oh, the runner is this many cc's, right? Okay, cool. But what is the average cross-sectional area? What is the minimum cross-sectional area? So there's a lot more to that than just shooting off at the hip and saying, yeah, we're going to hit 9,000 RPM. And that thing actually do
right.
it.
Custom engine, exotic materials. I've said this about 100 times probably this conversation, and that's the only way to describe this. And this is what it takes when you're doing something like that. Like it takes a freaking team of engineers and really smart people.
Yeah, and then the next step after we'll take a look at the CNC and we'll kind of see. But once these go through the CNC, they'll be sent off. Race Tech will take them.
These have a whole trip ahead of them. A whole trip ahead of them.
A trip around the
world. They have to go to Race Tech for piston design.
Hogan's. Hogan's is going to design a custom intake manifold with dual 4500 series throttle bodies for us. So it's not going to be.
So for those people who are like LS diehards and that don't know what a 4500 is, this is a 4500. So this engine here is going to require so much air that we need a custom intake manifold that will have 2 of these flanges, and then we'll probably end up using the Wilson, right? The Wilson is the baddest, most flowing 4500 throttle body, and then that's up to me after this is trying to figure out how to make a drive-by-wire.
That's yours.
Yeah.
I'm gonna do it
mechanical on your push-pull cable on your boat throttles, right? Yeah.
I'll have you stand in there and just. But yeah, once they're done and everything, we'll send it off to Hogan's. We'll have an intake manifold engineered for it. We'll tell him targets, and then he'll know, runner length, plenum volume, all that stuff that he has to achieve with that design to hit our target RPM.
Because that's, again, nothing off the shelf. That is engineered based off of what we give them on the heads, the RPM range that we're like, there are probably 15 or 20 pieces of information that Hogan's is going to need to even start the design work on the intake manifold, and then he's got to manufacture it.
Correct. So then it'll be CNC, aluminum piece, one of a kind. So that's that pretty much. I think we covered everything.
Yeah. Should we go look at the CNC and see the next stop for these CIV heads? Yes, the butcher shop, pretty much.
Yeah. 20 pounds.
So we are at the CNC. We're at the point now where we need to get some measurements and figure out the shape and the design and do the whole process to cut those heads. because I'm sure a lot of you guys looked and you're like, God, those ports look so small, but that's because that is as cast, that is raw. Eventually, it is gonna wind up something like this, but this is a hand port. So we need to put it in the CNC. Yeah, what do you, actually, I don't know. I don't wanna say what we're doing because I was lost about 10 minutes ago.
Okay, so the process for this is basically Cesar Talese from CT Porting. He got one of the porter's castings, and this cylinder head, this porter's casting is actually, this is the Ford SC2 cylinder head. So what that means is the bore spacing, the coolant, and all of that other stuff is actually supposed to work on a Ford. The Ford has a 4-380 bore spacing. So let me rotate this real quick. Yeah. So what that means, if that 4-380 bore spacing, the center of each combustion chamber is 4-380, and then 4-380, 4-380, 4-380. An LS has a 4-400 bore spacing. So what he did is he started out with the Ford cylinder head. He developed a chamber for us, or intake port. He's, you know, he'll do one, he'll see if it's he's happy with it. If not, he'll make some changes. And then, you know, make sure that there's great velocity, the valve job, the transition in that chamber, the chamber design itself, all of that, and then the exhaust and all, you know. So he goes through there and he does several renditions. If he's not happy, he'll put epoxy back in some of the areas and improve the chamber, improve the flow, all of that. So what he did is he came up with a port program that he was happy with on this, and that's the port program there that we'll be using on Matt's cylinder heads. It actually has a little wing on the short side turn, and that will help with velocity around that short side turn.
And yeah, he looks like that was put in with epoxy
so
after to try something. Yeah,
he blended it back, and I think this port was the first one he started with, and then he made some changes and he went over to this one. And then on the exhaust side,
and this is the plate that you were having to modify.
Well, so I made offset pins because it's a Ford head. Yeah. This is my LS plate.
Right. Yeah.
So I had to shift it over to line up for the Ford. And then, so this is the exhaust port that'll be the final exhaust port.
Holy moly!
Yeah.
That thing is monster. So how it starts out, how it winds up. That's a lot of material. Right. We were estimating close to 15 pounds of material coming off.
I don't know what it's going to be, but I hope it's a lot because those things are heavy.
Yeah, they are so heavy.
Moving them around is like holy.
Even just the deck thickness of these is freaking ridiculous.
Right. So, but yeah, if you look here on that short side turn, you can see that.
Oh yeah. And with the wing, that's the plan because that's the That's the chamber shape that we're going to be replicating, right?
This gives us the volume that we need. It gives us the cross-sectional area that we need. And then to help that airspeed, we don't want a lazy port because it's a big port. So to help that airspeed, he put that wing in there and it'll help that airspeed at lower transition because, you know, when you're transitioning from gears and stuff and the RPM is dropping back, you want that airspeed to be there. The airspeed is based off of piston speed and demand of that engine. So if you lower your RPM, you're gonna have less airspeed just because the piston speed is slower. So what we start out with is basically, we'll digitize each port that he's finished up here, and it'll turn into something like this. Right now, it's kind of a rough. We still have to go through. You can see like in here, in this area here, there's some editing that has to happen. So to match his port, we'll end up editing all of this.
And then you are the guy to do that smoothing, and you do all that in the software yourself.
I'll go in there to the software, or Aaron will go into the software. One of us will go into the software. We'll both go through here, and then we'll run one of the ports to make sure that it looks correct, and that then we'll put it back on the flow bench. We'll flow it. I'll get Caesar's blessings on it and everything like that as well. So we keep him in the loop with all of that. And then we'll run it on Matt's heads, and then we'll have our final port program, and then that'll be what we run.
And we gotta get it right because it's not like we're just getting another set of these heads tomorrow. Exactly. They are on no one's bench. They're on no one's shelf.
No, we should probably order another set.
Yeah, like these are them. That's it. Right. So let's not screw it up.
Yeah. So one of the benefits of having the CNC though is I get to have all of this data now, and it's not just so much the port program and everything, but I can go in, I can look at the cross-sectional area, I can go look at the distance from, so say if I go like that, I can give that distance to seat. So 6 inches, that's the distance from the flange to the seat. I can give that to Hogan's and tell them, look, this is the runner length of that cylinder head. And then they can do math and figure out, okay, this is our target RPM. This is the distance to seat. This is how much intake runner length we need now to actually achieve that. I can give them cross-sectional area and every single one of these planes here. And then I can add all of those planes up, the cross-sectional area, divided by how many planes, and get an average cross-sectional area as well. And then I can do that for the exhaust port as well. So I have a ton of data to work with when we're doing an engine development program. And we're not just shooting from the hip and saying, oh, well, the intake runner's, you know, whatever CC and the valve size is this. It's a lot more involved and critical than just, you know, buying something off the shelf and being like, yeah, we're gonna make 1,000+ horsepower. I don't think so.
Yeah.
You know,
and that's the difference. Like this is a development program because a lot of this stuff is something that Semir and I, both of us, have not done before. We're figuring it out as we go. But we want some longevity in it. We want to put time, effort, energy, and money because I've always been huge naturally aspirated fan, but never quite had the direction. And this is different. Like this requires a freaking team. So to be here and be working with this port program and then have plans to be going with different camshafts and profile, like the plan is to step and learn and create something and do better and hopefully do another one of these at some point, have a spare, right?
We'll have a spare. And then so again, one of the things is when we're developing this, having as much data as possible is critical, because when I call my guys at Comp Cams, you know, and we get them involved and stuff like that, I'm going to tell them, look, this is the runner volume, this is our target, this is this. So we give them as much data to work with, and we might have to order 1 or 2 or maybe even 3 camshafts to get it perfectly right. You know, like when you're doing something like this, it's not just going to happen the first time. We might get close, but we might be able to just tweak it just a little bit and be able to make it better. So
and in the naturally aspirated world, a little bit is a lot.
Right.
You don't just crank up the boost and be like, forget about it, it's fine. You're like, in this world, a camshaft profile could be huge, freaking huge.
Yeah, when you start talking 2 horsepower per cubic inch and above that, it's little changes are critical.
2 horsepower per cubic inch.
So
nuts.
Yeah, so like I said, we're gonna have multiple camshafts. We're gonna do some other, you know, just test, figure it out, have it on the dyno. And then one of the things that I'm working on getting actually is combustion analysis in the dyno cell as well.
That's right.
I don't know if we'll have time for that. I don't know if Matt's got enough patience. He's been pretty patient so far. I don't know. He'll probably be like, okay, this is great.
Yeah. That's enough power, dude. Let's put the thing in. Let's go.
I want to drive it.
I know.
Right,
and we should go check out the dyno room too.
Absolutely.
Yeah, absolutely. We should go check that out. And your boys were just in here getting this thing rigged up. Looks like some sort of an LS.
So this is a 490 LS for Bailey Campbell. So we're getting this thing on the dyno tonight. We're gonna run it for her, break it in, get some numbers on it, some data, and then we'll ship it out to her tomorrow, and she'll probably have it in she's really fast. She gets this engine in like 6 hours, I think, maybe even less than that.
Yeah. Might be running end of day tomorrow in the truck.
Amazing.
Yeah. You get to see all the little things that have been fabricated to work on the dyno over the years that has changed, modified and.
Yeah, we're still going to clean it up, but one of the things that we'll do with your engine when we have it on the dyno, we'll have EGTs in each cylinder, we'll have wide bands in each cylinder. So the dyno has the ability to do all of that and then data log all of that, but also the ECU that you use has the ability to do that too.
And that was one thing too, I've been hammering with, especially Jay, my tuner, and Semir, is that I want 8 EGTs. That is, in my opinion, that's the way to do it. And that's the way that nothing's safe in this world, especially at 9,000 RPM, but you're at least ensuring yourself to be a little bit more on the safe side, especially because there's going to be a lot of power to be had from individual cylinder tuning. Right now, we do a little bit with the EGT sensors, but with boost, like the gains, we noticed there was a big difference with our EGTs. We did a bunch of cylinder fueling. Did it make that much more power? No. Is the engine a little bit happier and longevity-wise? Yeah, but there are a lot of gains to be had with individual cylinder tuning with naturally aspirated stuff, especially on the C8 engine.
Yeah, and one of the things like we were talking about previously is the combustion analysis too. So with the combustion analysis, you can actually meter where peak cylinder pressure is at from timing or cam events as well. So if we have the time to get it on and get it operating for your engine, I would love to do that. It's just the cost of it and everything and the time schedule that we're on, but we're shooting for it.
A lot of project, a lot of things in the fire right now, that's for sure.
We're juggling a lot, so we'll move forwards with it and hopefully we have it on here. But basically the way the combustion analysis works is it has a probe that goes into this chamber, so it'll see the peak spike of cylinder pressure, and we can time that. We can see detonation, we can see what's going on in there. So it's like having a camera or being inside there and actually seeing that flame front, and then seeing if that flame front stays in control, where that intake valve is opening, exhaust valve is opening, the intake valve is closing, how that influences the cylinder pressure and all of that. So
it's an added tool, and you would run that with EGTs ADGTs, 802s, and
Yes.
the cylinder analysis.
Yes.
That's
And then-
another tool.
and then-
And then what if you're not happy with it? Is that like a camshaft change, a
It could
valve
be a
lash
camshaft
change?
change. It could be timing, so you'll see if it's detonation,
Right.
you know, and then every engine has a little bit of detonation, but the amount of detonation, the frequency of that detonation, and then see where the cam timing is. So if we see like the cam is closing at this certain degree, but we've already missed the opportunity to get that peak cylinder pressure, then we know we've overcammed it. So then we could back it off and then get some more peak cylinder pressure, make more power, back off on the duration and everything, and then, you know, make those changes, or advance and retard the camshaft as well and play around with it.
And those are potentially big gains. Like that's where you see 25 horsepower here, 15 horsepower there, 50 here. Like those things add up very, very quickly.
Yeah, so I mean, your dyno session might turn into weeks long.
As long as I'm here to listen and watch, dude, I know. Dude, you know what's so funny? I hate having my car. I've never had any of my engines on an engine dyno, but I hate having my car on the wheel dyno. I hate being there. Even though I gotta be the guy, because I'm the attentive guy. I'm watching the blower belt, I'm fixing spark plug wires, we want to change the valve lash, checking the oil, breaking in the motor, checking the coolant pressure, like, you know, all the stuff that you do when you have your car on the dyno for the first time, but I hate it. It's so nerve-wracking, and this guy just sits here in this room and turns things to 9,000 RPM, like, I want to be here for that, but I'm gonna be so scared.
For me too, let's not, I want it to be successful, but the probability of a failure is always there.
Yeah,
so it's
no
like,
matter what.
You're especially when you're pushing something to that level and that RPM, and you're kind of like, you know, you're going for every single last piece of horsepower. You're doing stuff fails. It's mechanical. You know, you might have a lifter take off, and that lifter just causes chaos within the engine. So it's just like
that's freaking racing. That's it.
The game.
Yeah.
We're gonna hope and we'll build it to the best of our ability. We'll use the highest quality products, and that's gonna ensure that we have the highest probability of success. But
that's all we can do.
Yeah.
That's it. That's it. Well, these boys are getting ready to get this thing going on the dyno. Thank you so much for your time, Semir.
Well, I appreciate you stopping by.
Yeah.
I appreciate you working with us.
And this is the first time that I've seen these heads. The first time I've seen the block. I haven't seen any of these parts. So before we fired up the GoPro, I was a happy freaking schoolgirl, that's for sure. And I'm gonna just poke around here and enjoy touching all these badass freaking parts. And then I'm gonna go back and start doing some welding on the C8, but hell freaking yeah.
Take care, guys.